The speed of light, the conservation of energy and momentum, the second law of thermodynamics, the properties of matter under extreme conditions, these are not obstacles to be overcome by cleverness or determination, but facts to be acknowledged and worked with. Engineering is the art of achieving goals within the constraints imposed by nature, and the greatest engineering achievements are those that push close to the limits without exceeding them, extracting maximum performance from the available resources and the permissible physics. The exploration of space, whether to Pluto, to Proxima Centauri, or anywhere else, is an exercise in understanding and respecting these limits while seeking the paths that remain open within them. The journey to Pluto required 9.5 years, and the coordination of thousands of people over decades, the deployment of cutting-edge technology, and the acceptance of a one-time flyby with no possibility of return or extended observation. The journey to Proxima Centauri, if it is ever attempted, will require far more. Energy on scales that challenge the output of entire civilizations, technologies that do not yet exist and may not be possible, timescales that exceed human lifespans and institutional continuities, and a willingness to accept uncertainty, risk, and the possibility of failure on a profound scale. The difference between the two is not merely quantitative, but qualitative, reflecting a threshold beyond which the familiar methods and assumptions of spaceflight break down and new paradigms are required. Whether that threshold can be crossed and what lies beyond it remains an open question. The universe is vast, and the distances between stars are a measure of that vastness, a reminder that the cosmos is not designed for easy access or human convenience. The light from Proxima Centauri, emitted 4.24 years ago, reaches us now, carrying information encoded in its spectrum, its polarization, its variations over time, and from this light, we have learned much about the star and its planets. But the light travels alone, and we remain here, bound to our solar system by the constraints of energy, time, and the relentless arithmetic of the rocket equation, contemplating a gulf that may never be bridged by anything more substantial than electromagnetic waves and the trajectories of robotic emissaries, if even that. The impossibility of reaching Proxima Centauri, and to a lesser extent Pluto, is not a counsel of despair, but a recognition of the scale and structure of reality, a foundation for understanding what is achievable and what lies beyond the horizon of the possible. In that understanding lies the beginning of wisdom about our place in the universe, the limits of our reach, and the choices we face as a species capable of asking such questions, but not yet capable of answering them through direct experience. The distance between Earth and Pluto varies between approximately 4.7 billion kilometers at its closest approach and 7.5 billion kilometers at its most distant configuration, a range that captures the eccentric geometry of Pluto's orbit and underscores the first layer of difficulty inherent in reaching even this comparatively nearby object. When New Horizons crossed the Pluto system in July of 2015, it had been traveling for 9.5 years, covering a distance of roughly 5 billion kilometers, having been launched with a velocity exceeding 16 kilometers per second relative to Earth, making it the fastest spacecraft ever dispatched from our planet at the time of its departure. That velocity, extraordinary by the standards of human engineering, was achieved through the combined effort of an Atlas V rocket's chemical propulsion and a gravitational assist from Jupiter, a maneuver that added approximately 4 kilometers per second to the probe's heliocentric velocity and shaved years from the total flight time. Without that gravitational slingshot, the mission would have required either a much larger launch vehicle or a flight duration extending well beyond a decade. And even with these advantages, New Horizons arrived at Pluto moving so quickly that it could do nothing but pass through the system in a matter of hours, its instruments capturing data during a narrow window of opportunity before the dwarf planet receded forever into the distance behind it. This inability to stop, to enter orbit, to linger and explore at leisure, is not an incidental limitation of mission design, but a direct consequence of the fundamental physics governing motion in space. To slow down requires energy, and in the absence of an atmosphere thick enough to provide aerodynamic braking, that energy must come from propellant carried aboard the spacecraft itself. The relationship between the change in velocity achievable by a spacecraft, known as delta V, and the mass of propellant required is described by the Tsiolkovsky rocket equation, which states that delta V equals the effective exhaust velocity of the propellant multiplied by the natural logarithm of the initial mass divided by the final mass. This logarithmic relationship means that the mass of propellant grows exponentially with the desired change in velocity, and even modest increases in delta V demand disproportionately large quantities of fuel. For a spacecraft traveling at 16 kilometers per second, reducing its speed to zero, or relative to Pluto, would require a delta V of 16 kilometers per second. And if that spacecraft were using conventional chemical propulsion with an exhaust velocity on the order of 4 kilometers per second, the mass ratio, the ratio of initial mass to final mass, would need to be approximately 54 to 1. In practical terms, this means that for every kilogram of payload and structure remaining at the end of the burn, 54 kilograms of propellant and tankage would need to have been present at the start, a ratio that quickly becomes untenable when scaling up to realistic mission architectures. The mass ratio problem compounds at every stage of the mission. To accelerate that enormous mass of propellant and structure up to 16 kilometers per second in the first place requires an even larger initial mass at launch, creating a recursive burden in which the fuel needed to carry fuel dominates the design. New Horizons avoided this trap by committing to a flyby trajectory from the outset, accepting that the spacecraft would never slow down, never return, and never revisit the target, trading comprehensive exploration for the possibility of reaching Pluto at all within a human timescale. Even so, the spacecraft's mass at launch was only 478 kilograms, a figure that reflects aggressive engineering choices to minimize weight at every opportunity, from the selection of lightweight instruments to the use of a radioisotope thermoelectric generator for power instead of solar panels, which would have been too large and massive to function effectively at Pluto's distance from the Sun. The entire mission was an exercise in subtraction in determining what could be left behind or made smaller, lighter, more efficient in order to fit within the performance envelope of available launch vehicles and propulsion systems. The energy required to reach Pluto is derived almost entirely from chemical reactions, specifically the combustion of hydrazine-based fuels with nitrogen tetroxide or similar oxidizers, reactions that release energy by breaking and forming molecular bonds, a process governed by the electron configurations of atoms and the electromagnetic forces binding them. The maximum energy density achievable with chemical propulsion is constrained by the strength of these bonds, which in turn is determined by fundamental constants of nature, such as the fine structure constant and the mass of the electron. There is no way to extract more energy from a given mass of chemical fuel than quantum mechanics and chemistry allow. And while engineering improvements can optimize combustion efficiency, nozzle design, and mass distribution, these refinements operate within narrow margins around a fixed upper limit. The exhaust velocities of the best chemical rockets hover around 4 to 5 kilometers per second, and this figure has remained largely unchanged for decades, not because of a lack of innovation, but because it reflects a physical ceiling inherent in the chemistry itself. This ceiling becomes a binding constraint when considering the energy requirements for interstellar travel. Proxima Centauri, the nearest star to our Sun, lies approximately 4.24 light-years away, a distance equivalent to roughly 40 trillion kilometers, or about 8,000 times the distance from Earth to Pluto at its farthest. The scale of this gulf cannot be overstated. If the distance to Pluto is already severe enough to demand a decade-long journey with our fastest spacecraft, then the distance to Proxima Centauri, multiplied by that factor of 8,000, implies travel times measured not in years or decades but in millennia unless the velocity of the spacecraft can be increased proportionally. To reach Proxima Centauri in, say, 40 years, a duration comparable to a human career or a lifetime, a spacecraft would need to travel at roughly 10% of the speed of light, or about 30,000 kilometers per second. This is nearly 2,000 times faster than New Horizons. The kinetic energy of a spacecraft moving at 10% of light speed scales with a square of the velocity, meaning that the energy per unit mass is not 2,000 times greater, but 4 million times greater than that of New Horizons. For a spacecraft with a mass of even a single ton, the kinetic energy at 10% of light speed would be approximately 4.5 times 10 to the 17th joules, equivalent to the energy released by more than 100 megatons of TNT, roughly double the yield of the largest nuclear weapon ever detonated. Achieving such velocities with chemical propulsion is not merely impractical, but impossible in any meaningful sense. The mass ratios required would be so extreme that no conceivable structure could contain the necessary propellant. To accelerate a 1-ton payload to 10% of light speed using a chemical rocket with an exhaust velocity of 4 kilometers per second would require a mass ratio on the order of 10 to the power of 3,000, a number so large that it exceeds the number of atoms in the observable universe by incomprehensible margins. The spacecraft's initial mass would need to be greater than the mass of all matter in existence, a clear absurdity that underscores the inadequacy of chemical propulsion for interstellar missions. Even if we consider more advanced propulsion concepts, such as nuclear thermal or nuclear electric propulsion, which can achieve exhaust velocities of 10 to 100 kilometers per second by heating propellant with a nuclear reactor or accelerating ions with electric fields, the mass ratios, while improved, remain prohibitively large. A nuclear electric propulsion system with an exhaust velocity of 50 kilometers per second would still require a mass ratio of approximately 400,000 to 1 to reach 10% of light speed, a figure that remains entirely beyond the bounds of feasibility. The alternative to carrying propellant is to find ways of imparting momentum to the spacecraft from external sources. One proposal that has received serious theoretical attention is the concept of a laser-driven light sail, in which a large, lightweight reflective sail is pushed by the momentum of photons emitted from a powerful laser array stationed in Earth orbit or on the lunar surface. Photons, despite having no rest mass, carry momentum proportional to their energy divided by the speed of light, and when they reflect off a surface, they transfer twice their momentum to that surface. A sufficiently powerful laser, operating continuously over a period of minutes or hours, could in principle accelerate a light sail to a significant fraction of light speed without the spacecraft needing to carry any propellant at all. The energy would come from the laser installation, which could be powered by solar panels, nuclear reactors, or other stationary energy sources with access to large amounts of power. The Breakthrough Starshot Initiative, announced in 2016, has proposed exactly this approach, envisioning a swarm of small probes, each massing only a few grams and equipped with a sail several meters across, accelerated to 20% of light speed by a ground-based laser array with a total power output of 100 gigawatts. The engineering challenges involved in such a system are formidable and, at present, unresolved. A laser array with a power output of 100 gigawatts would be among the largest energy installations ever constructed, requiring either vast fields of solar panels or a dedicated nuclear power complex. And the laser itself would need to be phased coherently across many individual emitters to focus the beam tightly enough to remain effective over the vast distances involved. Even a slight divergence in the laser beam would cause the intensity to drop off with the square of the distance, and by the time the spacecraft had traveled even a small fraction of the distance to Proxima Centauri, the beam would have spread so widely that the majority of photons would miss the sail entirely. Correcting for this requires either an enormous initial beam diameter or adaptive optics capable of compensating for atmospheric distortion and diffraction effects in real time, both of which add layers of complexity and cost. The sail itself must be extraordinarily lightweight, with a mass per unit area on the order of grams per square meter, yet also strong enough to withstand the intense thermal and mechanical stresses imposed by the laser. At the intensities required, the sail material would be heated to temperatures of hundreds or thousands of degrees, and any imperfections, wrinkles, or variations in reflectivity could lead to differential heating, warping, and ultimately structural failure. The material science needed to produce such a sail does not yet exist in deployable form, and it remains uncertain whether any material can meet the conflicting demands of low mass, high reflectivity, high thermal tolerance, and structural integrity. Even if these challenges were overcome, the light sail approach suffers from an intrinsic limitation. It provides no means of slowing down. A spacecraft accelerated to 20% of light speed by a laser would continue at that velocity indefinitely unless acted upon by another force, and in the interstellar medium, there are no convenient sources of braking. One could propose a second laser array at the destination, positioned to decelerate the spacecraft by reflecting photons off the opposite side of the sail, but this would require the establishment of infrastructure at Proxima Centauri in advance of the mission, an obvious impossibility. Alternatively, the spacecraft could carry a second sail oriented to catch light from Proxima Centauri itself as it approaches, but the luminosity of Proxima Centauri, a red dwarf with only about 1/7 the diameter of the Sun and roughly 1/600 the luminosity, would be far too faint to provide meaningful deceleration over reasonable distances. The intensity of starlight falls off with a square of the distance, and even at distances of billions of kilometers from Proxima Centauri, the radiation pressure would be negligible compared to the momentum of a spacecraft moving at relativistic speeds. Without a method of braking, any interstellar probe would be limited to a flyby, passing through the target system in a matter of hours or days, and transmitting whatever data it could gather during that brief window before receding into the darkness beyond. The transmission of that data presents its own profound difficulties. At a distance of 4.24 light years, a radio signal traveling at the speed of light would take 4.24 years to reach Earth, meaning that any observation made by the spacecraft would not be received until more than 4 years after the event occurred. This delay is irreducible, a consequence of the finite speed of light and the vast distances involved, and it imposes severe constraints on the design and operation of interstellar missions. The spacecraft cannot be piloted in real time. Every command sent from Earth will arrive years after it is transmitted, by which time the circumstances that prompted the command may have changed beyond recognition. The probe must therefore be autonomous, capable of making decisions about observations, course corrections, and data prioritization without input from human controllers, and it must be robust enough to continue operating for decades in an environment where repair and maintenance are impossible. The communication system itself must be capable of transmitting across interstellar distances with sufficient power and directionality to ensure that the signal can be detected above the background noise of the cosmos. The intensity of a radio signal decreases with the square of the distance, so a signal that is strong and clear at the distance of Pluto becomes vanishingly faint at the distance of Proxima Centauri. To maintain a detectable signal, the spacecraft must either transmit at higher power, which requires more energy, and larger power sources, or use a highly directional antenna, which requires precise pointing accuracy maintained over interstellar distances. The power requirements for interstellar communication are daunting. New Horizons, operating at Pluto with a transmitter power of 12 watts and a high-gain antenna 2.1 meters in diameter, was able to achieve data rates of only a few hundred bits per second when transmitting back to Earth's deep space network. At the distance of Proxima Centauri, the received signal strength would be reduced by a factor of more than 60 million, rendering communication effectively impossible with similar hardware. To achieve even a minimal data rate of 1 bit per second at interstellar distances would require either a dramatic increase in transmitter power, which in turn demands larger power sources and thermal management systems, or an increase in antenna size, which adds mass and complexity. A realistic interstellar probe would likely need a power source capable of delivering tens or hundreds of watts continuously for decades, and the only known technology that can meet this requirement without relying on sunlight, which becomes negligibly weak beyond the outer solar system, is a radioisotope thermoelectric generator, or in more advanced concepts, a small nuclear reactor. Both options come with their own challenges, including the limited availability of suitable isotopes, such as plutonium-238, the decay of power output over time, and the need for radiation shielding to protect sensitive electronics. The electronics themselves must be designed to survive not only the cold and vacuum of space, but also the intense radiation environment encountered during the journey. In interplanetary space, radiation comes primarily from the solar wind, a stream of charged particles emitted by the sun, and from galactic cosmic rays, high-energy particles originating from outside the solar system. The intensity of solar wind decreases with distance from the sun, so a spacecraft traveling to the outer solar system or beyond will experience less direct exposure to solar radiation. But galactic cosmic rays are present throughout the galaxy and cannot be avoided. These particles, predominantly protons and heavier atomic nuclei, carry enormous energies, often measured in billions or trillions of electron volts. And when they collide with matter, they can penetrate deeply, ionizing atoms, breaking molecular bonds, and causing cumulative damage to materials and electronic components. Semiconductors are particularly vulnerable. A single high-energy particle passing through a microchip can deposit enough charge to flip a bit in memory, corrupt data, or even permanently damage the circuit, a phenomenon known as a single-event upset or single-event latch-up. Over the course of a multi-decade interstellar mission, the cumulative dose of radiation would be substantial, and without adequate shielding or error correction mechanisms, the spacecraft's computer systems would gradually degrade and fail. Shielding against high-energy cosmic rays is difficult because effective shielding requires significant mass, and mass is the enemy of all spacecraft design. Materials with high hydrogen content, such as water or polyethylene, are relatively effective at stopping or slowing cosmic rays, but encasing a spacecraft in a thick layer of such material adds weight that must be accelerated, reducing the achievable velocity for a given propulsion system. There's a trade-off between protection and performance, and for interstellar missions where every gram counts, the balance tilts heavily toward minimizing mass, leaving the spacecraft more exposed. Redundancy can mitigate some of the risk. Critical systems can be duplicated or triplicated so that if one component fails, others can take over. And data can be encoded with error-correcting codes that allow the reconstruction of information even if some bits are corrupted. But redundancy itself adds mass and complexity, and there is no perfect solution, only a careful weighing of risks and resources. The interstellar medium, though often described as a vacuum, is not entirely empty. It contains a diffuse distribution of gas and dust, with densities on the order of 1 atom per cubic centimeter in typical regions, though densities can be higher in molecular clouds and lower in the voids between them. At the velocities required for interstellar travel, even individual atoms become hazards. A hydrogen atom encountered by a spacecraft moving at 10% of light speed would impact with a relative kinetic energy of approximately 7,000 electron volts, enough to sputter away surface atoms, degrade optical coatings, and erode structural materials over time. Larger particles, grains of dust with masses of micrograms or milligrams, would strike with energies equivalent to macroscopic projectiles, capable of puncturing thin membranes, damaging instruments, or even catastrophically destroying the spacecraft if the impact occurs in a critical location. The probability of such an impact increases with the cross-sectional area of the spacecraft and the distance traveled, and over a journey of trillions of kilometers, even rare events become statistically significant. A light sail with an area of several square meters traveling through the interstellar medium for decades would inevitably accumulate impacts, each one contributing to a gradual degradation of the sail's reflectivity and structural integrity, reducing the efficiency of any future braking maneuvers and increasing the risk of failure. At higher velocities, the problem intensifies. The kinetic energy of a particle scales with the square of the velocity, so a spacecraft traveling at 20% of light speed encounters interstellar hydrogen with 4 times the energy per atom compared to one traveling at 10%. At 50% of light speed, the energy increases 16-fold. Near the speed of light, the impacts become so energetic that they can trigger nuclear reactions, transmuting atoms in the spacecraft's structure and producing secondary radiation, including neutrons and gamma rays, that further damage materials and electronics. The spacecraft's forward-facing surfaces would effectively be subjected to continuous bombardment by a particle beam, a form of erosion that no known material can withstand indefinitely. Proposals to address this include placing a sacrificial shield at the front of the spacecraft, an expendable layer designed to absorb impacts and protect the more delicate components behind it. But such a shield must itself be accelerated, adding to the overall mass, and it must be thick enough to stop or slow the most dangerous particles without becoming so massive that it defeats the purpose. The optimal design depends on the expected density of the interstellar medium along the trajectory, which is difficult to predict with precision and may vary over time as the spacecraft passes through different regions of space. The distance to Proxima Centauri is not merely a number, but a physical expanse that must be crossed in time, and time itself becomes a constraint that shapes the feasibility of interstellar exploration. For a spacecraft traveling at 10% of light speed, the journey to Proxima Centauri would take 42 years, and for a mission traveling at 5% of light speed, a more conservative estimate given the engineering challenges, the duration extends to 85 years. These timescales exceed the typical human lifespan and certainly exceed the working lifespan of most technologies. The computers, sensors, and mechanical systems aboard the spacecraft would need to function continuously for nearly a century without maintenance, repair, or replacement, a requirement that far surpasses the operational lifetimes of any spacecraft built to date. Voyager 1 and Voyager 2, launched in 1977, have been operating for more than 45 years as of 2023, a remarkable achievement, but they are now experiencing the gradual failure of instruments and subsystems as power from their plutonium 238 thermoelectric generators declines and components degrade from age and radiation exposure. Extending this operational lifetime by another factor of 2 or more, as would be required for an interstellar mission, is not simply a matter of building more robust hardware, but involves confronting the fundamental limits of material stability, electronic reliability, and the predictability of long-term failure modes. For a mission involving human passengers, the timescale problem becomes existential. A journey of 85 years is longer than a human life, meaning that anyone who departs on such a voyage would not survive to see the destination. The only possibilities are either to extend human lifespan dramatically through biological or technological intervention, to accept a multi-generational mission in which the descendants of the original crew complete the journey, or to place the passengers in some form of suspended animation or hibernation that slows or halts biological aging. Each of these options confronts obstacles that are at best speculative and at worst insurmountable. Life extension sufficient to allow a single individual to survive a century-long journey does not currently exist and would require advances in biology and medicine that remain theoretical. Multi-generational missions raise profound questions of social organization, resource allocation, and psychological sustainability. How does a community maintain continuity, purpose, and cohesion over multiple generations when the destination is an abstraction that no living member has experienced? The spacecraft would need to be large enough to support a viable population with sufficient genetic diversity to avoid inbreeding, and it would need to provide not only life support and food production, but also education, governance, conflict resolution, and meaning. The engineering of such a vessel, a closed ecosystem capable of sustaining human civilization for a century or more, is orders of magnitude more complex than any spacecraft ever built, and the social dynamics are entirely untested. Suspended animation, while a staple of science fiction, remains unproven as a practical technology. Hibernation, in the sense used by bears and other mammals, involves a reduction in metabolic rate and body temperature, but it does not halt aging entirely, and it has never been induced artificially in humans with reversible success. Cryopreservation, the freezing of biological tissue, can preserve cells and even small organisms indefinitely, but the process of freezing causes ice crystal formation that damages cell membranes and structures, and thawing often results in cell death. Vitrification, a technique that cools tissue rapidly enough to prevent ice formation, producing a glass-like solid state, has shown promise in preserving individual organs for transplantation, but scaling this to an entire human body and then successfully rewarming and reviving that body decades later is a challenge that has not been met. The energy required to maintain cryogenic temperatures for decades, the reliability of the refrigeration systems, the risk of power failure or equipment malfunction, and the unknown long-term effects of vitrification on neural tissue all contribute to a deep uncertainty about whether suspended animation can ever be a viable solution for interstellar travel. Even if the technological and biological challenges of long-duration spaceflight could be solved, the question of navigation and targeting remains acute. Proxima Centauri is not a stationary target, but a star moving through space with its own velocity relative to the Sun, and the exoplanet Proxima Centauri b, which orbits the star at a distance of roughly 7.5 million kilometers with a period of 11.2 days, is an even smaller and more dynamic target. To reach Proxima Centauri b specifically, as opposed to merely passing through the Proxima Centauri system, requires precise knowledge of the planet's position at the time of arrival, which in turn requires accurate predictions of its orbital parameters over the decades or centuries of the journey. Even small uncertainties in the initial trajectory, measured in fractions of a degree or meters per second, will accumulate over interstellar distances to produce enormous positional errors at the destination. A trajectory error of 1 part in a million at the start of the journey translates to a missed distance of 40 billion kilometers at Proxima Centauri, more than the diameter of the solar system. Correcting such errors en route requires the spacecraft to carry a propulsion system capable of making trajectory adjustments, which brings back the mass and propellant constraints that the light sail or other external propulsion concepts were meant to circumvent. The precision required for navigation is compounded by the limitations of astronomical observation. Proxima Centauri b was discovered in 2016 through the radial velocity method, which detects the gravitational tug of the planet on its host star by measuring tiny shifts in the star's spectral lines, shifts that indicate the star is moving toward or away from Earth as it orbits the common center of mass with the planet. This method reveals the planet's mass, orbital period, and orbital radius, but provides limited information about other parameters such as the planet's exact position along its orbit at any given time, its orbital inclination, or whether there are additional planets or debris in the system that could pose hazards to an incoming spacecraft. Direct imaging of Proxima Centauri b is extraordinarily difficult because the planet is more than 1 billion times fainter than its host star and separated from it by an angular distance of only 37 milliarc seconds as seen from Earth, an angle far smaller than the resolution limit of most telescopes and well within the glare of the star itself. Specialized techniques such as chronography, which blocks the star's light to reveal faint companions, or interferometry, which combines light from multiple telescopes to achieve higher resolution, have made progress in detecting and characterizing exoplanets, but the data remains sparse and uncertain. Designing a mission to arrive at a planet whose exact properties are poorly known is an inherently risky endeavor, and the risk increases with the distance and duration of the journey. The environment around Proxima Centauri introduces additional hazards that do not have analogs in the inner solar system. Proxima Centauri is a red dwarf, a class of stars that are smaller, cooler, and longer lived than the Sun, but also more active in terms of stellar flares and magnetic activity. Observations of Proxima Centauri have recorded frequent and powerful flares, bursts of radiation across the electromagnetic spectrum that can increase the star's brightness by factors of several or more within minutes, accompanied by the ejection of charged particles similar to solar coronal mass ejections, but potentially more intense relative to the star's baseline luminosity. These flares release enormous amounts of energy, much of it in the form of ultraviolet and X-ray radiation, which can strip away the atmospheres of planets in close orbits, particularly planets that lack strong magnetic fields to deflect the charged particles. Proxima Centauri b orbits within the star's habitable zone, the range of distances where liquid water could exist on a planet's surface, but this close proximity, only about 7.5 million kilometers, places it well within the range where stellar flares and particle radiation are most intense. A spacecraft or human outpost at Proxima Centauri b would be exposed to radiation levels far higher than those encountered in Earth's orbit, requiring heavy shielding or underground habitats to protect against both the chronic background radiation and the acute spikes during flare events. The question of whether Proxima Centauri b retains an atmosphere at all is uncertain. The combination of intense stellar radiation, particle bombardment, and the planet's proximity to the star suggests that any atmosphere it once had may have been partially or entirely eroded over the billions of years since the planet formed. Without an atmosphere, the surface would be exposed directly to the vacuum of space, to the full intensity of stellar radiation, and to the impact of micrometeoroids, making it an inhospitable environment for life, as we know it, and a challenging destination for human exploration. If an atmosphere does exist, its composition, density, and chemistry are unknown and could range from a thick, Venus-like envelope of carbon dioxide to a thin, Mars-like remnant, or something entirely unlike any atmosphere in our solar system. The lack of detailed information about the planet's surface conditions, magnetic field, rotation rate, and geological activity means that any mission to Proxima Centauri b would be in large part a leap into the unknown, with little ability to plan for contingencies or adapt to unexpected conditions once the spacecraft has been launched. The contrast between reaching Pluto and reaching Proxima Centauri is not merely one of degree, but of kind. Pluto, despite its distance and the challenges involved in getting there, remains within the gravitational and heliophysical domain of the Sun. The spacecraft traveling to Pluto can use the Sun's gravity for trajectory corrections, can rely on solar radiation for power if designed appropriately, and can communicate with Earth using established deep space communication networks with delays measured in hours rather than years. The environment at Pluto, while cold and dark, is relatively benign in terms of radiation and particle fluxes compared to the regions closer to the Sun or the interstellar medium beyond. Pluto itself has an atmosphere, albeit a tenuous one that freezes and sublimates with the planet's orbital cycle, and it has moons, geology, and surface features that can be studied with remote sensing and, in principle, with landers or rovers if future missions are developed. The obstacles to reaching Pluto are substantial, but not categorical. They are problems of engineering, cost, and mission duration, problems that can be addressed with existing or near-term technologies, and that have in fact been addressed successfully with the New Horizons mission. Proxima Centauri, by contrast, lies beyond the edge of the solar system's influence, in a region where the Sun is merely one star among many. Its gravitational pull negligible, its light no brighter than that of other distant stars. The interstellar medium separating us from Proxima Centauri is not an extension of interplanetary space, but a fundamentally different environment, one where the rules and assumptions that govern solar system exploration no longer apply. The distances are so great that light itself, the fastest phenomenon in the universe, takes years to traverse them, and no known propulsion technology can accelerate a macroscopic object to a significant fraction of light speed without confronting mass ratios, energy requirements, or material limits that render the endeavor impractical with current or foreseeable capabilities. The mission durations extend beyond human lifetimes, beyond the operational lifetimes of our most durable machines, and into timescales where the continuity of human civilization itself becomes a variable. The lack of infrastructure, the impossibility of resupply or repair, the communication delays that preclude real-time interaction, and the uncertainties about the destination all combine to create a situation in which interstellar travel is not simply difficult, but, for all practical purposes, beyond our reach. The term impossible requires careful qualification. It is not impossible in the sense of violating the laws of physics. There's no fundamental principle that forbids travel to Proxima Centauri, no theorem that proves it cannot be done. Photons make the journey routinely, and particles of matter, such as cosmic rays, traverse interstellar space at relativistic velocities. What is impossible is achieving interstellar travel with the energy sources, propulsion technologies, materials, and organizational capacities available to human civilization as it exists now, or as we can reasonably project it to exist in the near future. The gap between what is physically permissible and what is practically achievable is vast, and it is this gap that defines the impossibility under discussion. To close that gap would require not incremental improvements in technology, but transformative breakthroughs that alter the fundamental constraints we face. Breakthroughs in energy generation, propulsion efficiency, material science, life support, and perhaps even in our understanding of physics itself. One class of proposals that often arises in discussions of interstellar travel involves the use of nuclear fusion as a propulsion mechanism. Fusion, the process that powers stars, involves the combining of light atomic nuclei, such as hydrogen isotopes, to form heavier nuclei, such as helium, releasing energy in the process according to Einstein's equation relating mass and energy. The energy released per unit mass in fusion reactions is several million times greater than that released in chemical reactions, and the exhaust velocities achievable with a fusion rocket could, in principle, reach several percent of the speed of light, a dramatic improvement over chemical or even nuclear fission propulsion. A spacecraft powered by fusion could, in theory, achieve the velocities needed to reach Proxima Centauri within a human lifetime, and it could carry enough fuel to decelerate upon arrival, enabling orbit insertion or landing rather than a mere flyby. Fusion propulsion has been studied extensively in conceptual designs, such as Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, which proposed a two-stage fusion rocket using pellets of deuterium and helium-3 ignited by electron beams, achieving a top speed of 12% of light speed and a flight time to Barnard's star, a target slightly farther than Proxima Centauri of about 50 years. Despite decades of research, controlled nuclear fusion remains an elusive goal for terrestrial energy generation, let alone for propulsion. The challenge lies in achieving the conditions necessary for fusion to occur. Temperatures of tens of millions of degrees, densities high enough for nuclei to collide frequently, and confinement times long enough for the reactions to sustain themselves and produce more energy than is required to initiate and maintain them. On Earth, experimental fusion reactors such as tokamaks and inertial confinement facilities have succeeded in producing fusion reactions, but none has yet achieved net energy gain, the point at which the energy output exceeds the energy input. The ITER tokamaks, currently under construction in France and expected to begin operations in the late 2020s, aims to demonstrate sustained fusion with a net energy gain of 10 to 1. But even if successful, ITER will be a research facility, not a prototype for a practical power plant or propulsion system. The conditions required for fusion in a rocket engine, where the reaction must occur continuously, reliably, and efficiently in a compact, lightweight package exposed to the vacuum and radiation of space, are even more demanding than those for stationary power generation, and the engineering challenges of containing and directing the plasma exhaust, managing the intense neutron flux produced by deuterium-tritium reactions, and cooling the reactor components are formidable. Helium-3, often cited as an ideal fusion fuel because its reactions with deuterium produce fewer neutrons and therefore less damaging radiation, is extraordinarily rare on Earth, with naturally occurring concentrations measured in parts per trillion. Proposals to mine helium-3 from the lunar regolith, where it has been implanted by the solar wind over billions of years, or from the atmospheres of the gas giants, where it is somewhat more abundant, involve their own massive infrastructure investments and logistical challenges. The energy and cost required to extract, refine, transport, and store helium-3 in the quantities needed for interstellar missions may exceed the energy and cost savings gained by using it as fuel, creating a negative return on investment that undermines the rationale for its use. Alternative fusion fuels, such as deuterium alone or deuterium combined with tritium, are more accessible but produce higher neutron fluxes that complicate reactor design and increase the radiation exposure to spacecraft systems and, if present, crew. Even if fusion propulsion were to become a mature technology, the mass ratios and energy requirements for interstellar missions would remain substantial. A fusion rocket with an exhaust velocity of 3% of light speed, an optimistic figure based on theoretical calculations, would still require a mass ratio of approximately 50:1 to accelerate a payload to 10% of light speed and then decelerate to rest at the destination. For a spacecraft with a payload mass of 100 tons, the initial mass at departure would need to be 5,000 tons, the vast majority of which would be fusion fuel and the reactor and tankage needed to contain it. Launching such a mass from Earth's surface is beyond the capacity of any existing or planned launch vehicle, and even assembling it in orbit for multiple launches would be an undertaking of unprecedented scale and expense. The economic cost of such a mission, measured in trillions of dollars or more, would rival or exceed the gross domestic product of entire nations, and the political and social will to sustain such an investment over the decades required to design, build, and launch the mission is far from certain. The energy required to accelerate a spacecraft to relativistic velocities also raises questions about the availability and sustainability of energy resources on Earth. The kinetic energy of a 5,000-ton spacecraft traveling at 10% of light speed is approximately 4.5 times 10 to the 21st joules, equivalent to the total energy consumption of human civilization over several months. This energy must be supplied during the acceleration phase, which, to avoid crushing acceleration forces, would likely extend over weeks, months, or years, requiring sustained power outputs on the order of terawatts or more. Generating, storing, and delivering such amounts of energy would require energy infrastructure far beyond what currently exists, and the environmental and resource impacts of building and operating such infrastructure would be significant. The energy invested in a single interstellar mission could alternatively be used to address pressing challenges on Earth, from climate change mitigation to poverty alleviation, to the expansion of space-based infrastructure within the solar system, raising ethical and strategic questions about the allocation of resources and the priorities of a spacefaring civilization. Another class of interstellar propulsion concepts involves the use of antimatter, matter composed of particles with the same mass as ordinary matter, but opposite charge and quantum numbers. When matter and antimatter come into contact, they annihilate, converting their entire rest mass into energy with 100% efficiency, according to Einstein's mass-energy equivalence. The energy density of antimatter annihilation is the highest possible for any conceivable fuel, and a rocket using antimatter as its energy source could, in principle, achieve exhaust velocities close to the speed of light, enabling rapid interstellar travel with relatively low mass ratios. A few milligrams of antimatter, annihilated with an equal amount of matter, would release as much energy as several tons of conventional chemical fuel, and a spacecraft carrying kilograms or tons of antimatter could reach nearby stars within decades. The problem with antimatter propulsion is not theoretical but practical. Antimatter does not exist in significant quantities in nature and must be manufactured through high-energy particle collisions and accelerators, a process that is extraordinarily inefficient and expensive. Current production rates of antimatter at facilities such as CERN amount to only a few nanograms per year, and the cost per nanogram is estimated in the hundreds of millions of dollars, making the production of even a single gram of antimatter a task requiring decades or centuries at current rates and budgets. Scaling up production would require dedicated antimatter factories with particle accelerators far larger and more powerful than any in existence, representing an investment that, again, would be measured in trillions of dollars and would consume vast amounts of energy. The energy required to produce a given amount of antimatter is always greater than the energy that can be extracted from annihilating that antimatter, because the production process is inherently lossy, with much of the input energy dissipated as heat or lost in particle interactions that do not produce the desired antiparticles. This means that antimatter is not a source of energy, but a storage medium, a way of concentrating energy for later use, and the net energy balance of an antimatter-based mission is negative unless the antimatter is produced using energy sources that are themselves abundant and cheap. Which brings the discussion back to the challenges of terrestrial energy infrastructure. Storage of antimatter is another formidable challenge. Antimatter cannot be stored in ordinary containers because any contact with matter results in immediate annihilation. Instead, antimatter must be confined using electromagnetic fields that hold the antiparticles in a vacuum, suspended away from the walls of the containment vessel. For charged antiparticles such as antiprotons or positrons, this can be achieved using penning traps or other magnetic confinement devices, but these systems require continuous power to maintain the fields, and any failure of the power supply or the magnetic coils results in the loss of the stored antimatter. The confinement of neutral antimatter atoms, such as antihydrogen, is even more difficult because they do not respond to electric fields and can only be manipulated using the weak magnetic moments of their constituent particles, requiring extremely precise and stable magnetic field configurations. The longest that antimatter atoms have been confined in laboratory experiments is measured in minutes or hours, far short of the years or decades that would be required for an interstellar mission, and scaling up from individual atoms to macroscopic quantities introduces additional instabilities and risks. A containment failure in a spacecraft carrying kilograms of antimatter would result in a catastrophic explosion, releasing energy equivalent to multiple nuclear weapons and vaporizing the spacecraft and everything nearby. Proposals to mitigate the risks of antimatter propulsion include using the antimatter in very small quantities, annihilating only micrograms or milligrams at a time to produce controlled bursts of energy, or using it to catalyze fusion reactions rather than as a direct propellant, thereby leveraging the high energy density of antimatter while reducing the total quantity required. These hybrid concepts, sometimes referred to as antimatter catalyzed fusion or antimatter initiated microfusion, have been studied in various conceptual designs, but they remain speculative and face their own technical challenges in terms of reaction control, energy conversion efficiency, and integration with spacecraft systems. In all cases, the reliance on antimatter introduces a dependency on a resource that is prohibitively expensive, difficult to produce and store, and dangerous to handle, making it an unlikely candidate for near-term interstellar missions unless breakthroughs occur in multiple areas of physics and engineering simultaneously. The notion of generation ships, large spacecraft designed to sustain human populations over multiple generations during centuries-long interstellar voyages, recurs frequently in speculative discussions of interstellar colonization. The concept appeals to the imagination because it offers a potential solution to the problem of mission duration. If individuals cannot survive the journey, then a community can, with children born, raised, and educated aboard the ship, eventually taking over from their parents and grandparents to continue the mission. The generation ship would need to function as a self-contained biosphere, recycling air, water, and nutrients, growing food, managing waste, and maintaining mechanical and life support systems indefinitely. The population would need to be large enough to maintain genetic diversity and social complexity, typically estimated at several hundred to several thousand individuals, and the ship itself would need to be large enough to provide adequate living space, agricultural areas, manufacturing facilities, and storage for supplies and spare parts. The scale of such a vessel would dwarf any spacecraft ever built, and the mass, likely measured in millions of tons, would make propulsion and acceleration a challenge of even greater magnitude than for robotic probes. The biological and social dynamics of a generation ship are largely unknown because no human society has ever existed in complete isolation from the rest of humanity for more than a few years. Analogs such as isolated island communities, polar research stations, or submarine crews offer some insights into the psychology and social organization of confined groups, but these analogs are imperfect because they operate with the knowledge that resupply, communication, and eventual return to the broader world are possible. A generation ship crew would face the unique condition of knowing that they will never see Earth again, that their descendants will inherit a mission they did not choose, and that the success or failure of the mission depends on maintaining social cohesion, technological knowledge, and a shared sense of purpose across generations separated by decades or centuries. The risks of social fragmentation, cultural drift, loss of technical expertise, rebellion, or apathy among later generations, and the psychological burden of life in a confined, artificial environment are difficult to quantify but potentially catastrophic. A society that loses the knowledge or willingness to maintain critical systems, or that succumbs to internal conflict or resource depletion, would face extinction in the void, with no possibility of rescue or retreat. The ethical dimensions of generation ships are profound. The individuals who board the ship at launch do so voluntarily, but their children and grandchildren have no choice in the matter. They are born into a mission they did not select and cannot abandon. The imposition of such a fate raises questions about autonomy, consent, and the rights of individuals versus the goals of the collective. If later generations decide that the mission is not worth continuing, do they have the right to alter course, return to the solar system if possible, or simply halt the mission and live out their lives aboard the ship without proceeding to the destination? If resources are finite, as they inevitably are, what mechanisms exist to resolve disputes over their allocation, to enforce population limits, or to prevent overuse that would jeopardize the survival of future generations? These are not hypothetical questions, but central challenges that would need to be addressed in the design and governance of a generation ship, and they do not have obvious or universally acceptable answers. The alternative to multi-generational crewed missions is to limit interstellar exploration to robotic probes, accepting that human presence at the destination is not necessary for scientific discovery, and that remote observation, however delayed and limited, is sufficient. This approach sidesteps the biological and social challenges of long-duration human spaceflight and allows for smaller, lighter, and faster spacecraft, but it comes with its own trade-offs. Robotic probes lack the adaptability, intuition, and creativity of human explorers. They can only execute the tasks they are programmed to perform and cannot respond to unexpected discoveries or challenges with the flexibility that a human crew could provide. The data they return is constrained by the bandwidth of the communication link, the resolution of their sensors, and the predetermined priorities of their mission plan, all of which are fixed at launch and difficult or impossible to change once the probe is en route. A human crew, by contrast, can observe, analyze, and react in real time, can conduct experiments and investigations that were not anticipated, and can make decisions based on the full context of the situation, rather than limited telemetry and years-old instructions. The question of whether the increased scientific return from human exploration justifies the vastly greater cost, complexity, and risk is one that each society and each generation must answer for itself. And the answer is likely to vary depending on the resources, values, and priorities of the time. The fundamental barrier to interstellar travel is not primarily technological, but energetic. Energy, in the sense of physics, is the capacity to do work, to move matter, to overcome resistance, to change the state of a system. The distances involved in interstellar travel are so large, and the velocities required to traverse them in reasonable times are so high that the energy needed to accelerate a spacecraft to those velocities exceeds the output of all but the most powerful energy sources we can conceive. The energy must come from somewhere, from chemical bonds, from nuclear reactions, from the mass energy of antimatter, from sunlight captured and converted, from some as yet undiscovered process. Each of these sources has limits, set by the laws of thermodynamics, by the availability of fuel, by the efficiency of conversion, and by the constraints of engineering. The more energy a propulsion system requires, the more massive it becomes, because energy sources and energy storage systems have mass, and that mass must be accelerated along with the payload, creating a feedback loop that drives the total system mass upward. The rocket equation captures this feedback mathematically, showing that the mass ratio grows exponentially with the required change in velocity, and at the velocities needed for interstellar travel, the exponential function climbs so steeply that the solutions lie outside the realm of the feasible. Breaking free of the rocket equation requires finding ways to accelerate the spacecraft without carrying the energy source on board. And this is the motivation behind concepts like laser push light sails, magnetic sails that interact with the interstellar medium, or with particle beams fired from the solar system, and even more exotic ideas such as space-time manipulation or warp drives. The latter, based on speculative solutions to the equations of general relativity, propose creating a bubble of distorted space-time around the spacecraft that contracts space in front and expands it behind, allowing the spacecraft to effectively move faster than light relative to distant observers without ever exceeding the speed of light locally. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is the most well-known example of this concept, but it suffers from severe problems that likely render it impossible. The energy requirements, initially calculated to be equivalent to the mass energy of multiple solar systems, have been reduced in refined models, but remain astronomically large, far beyond any conceivable energy source. The drive also requires exotic matter with negative energy density, a form of matter that has never been observed and may not exist in nature, and even if it could be created, the quantities required and the stability of the space-time bubble are deeply uncertain. Furthermore, the physics of how such a drive would be initiated, controlled, or stopped, and how it would interact with the surrounding space-time and matter are poorly understood and may involve causality violations, singularities, or other pathologies that render the concept unphysical. Similar issues plague other speculative propulsion concepts such as wormholes, hypothetical shortcuts through space-time that could connect distant regions of the universe, allowing travel between them without crossing the intervening distance. Wormholes are solutions to the equations of general relativity, but like warp drives, they require exotic matter to stabilize them and prevent them from collapsing, and there is no evidence that such matter exists or that wormholes can form naturally or be constructed artificially. Even if a wormhole could be created, traversing it would involve passing through a region of extreme space-time curvature where tidal forces could be immense, potentially tearing apart any object that attempted the passage, and the wormhole itself might be unstable, subject to perturbations from quantum fluctuations or the passage of matter and energy that could cause it to pinch off or evaporate. The distance that a wormhole could span, its size, and the energy required to create and maintain it are all unknown, and the possibility that wormholes could be used for time travel, with the attendant paradoxes and causality violations, raises fundamental questions about the consistency of physical law. The speed of light, approximately 300,000 kilometers per second, appears in the structure of physics not as an arbitrary limit, but as a fundamental constant that relates space and time, energy and momentum, and underlies the causal structure of the universe. According to special relativity, no object with mass can be accelerated to the speed of light because the energy required to do so increases without bound as the velocity approaches light speed. As a spacecraft accelerates closer and closer to the speed of light, its relativistic mass, the effective mass as measured by the energy required to accelerate it further, increases, and the incremental change in velocity for a given expenditure of energy decreases, approaching zero as the velocity approaches the speed of light. This means that even with unlimited energy, a massive object cannot reach the speed of light, let alone exceed it, and the energy required to accelerate a macroscopic object to, say, 99% of light speed is so large that it becomes comparable to the rest mass energy of the object itself. For a 1-ton spacecraft, reaching 99% of light speed would require adding kinetic energy equal to approximately 7 times the rest mass energy of the spacecraft, equivalent to the energy released by annihilating 7 tons of matter and antimatter, a quantity far beyond any realistic fuel load or energy source. Relativistic effects also introduce complications for navigation, communication, and the experience of time aboard the spacecraft. At velocities approaching the speed of light, time dilation, a consequence of special relativity, causes time aboard the spacecraft to pass more slowly relative to time on Earth. For a spacecraft traveling at 90% of light speed, time aboard the spacecraft passes at only about 44% the rate of time on Earth, meaning that a journey that takes 47 years by Earth's clocks would feel like only about 21 years to the crew. At 99% of light speed, the time dilation factor increases to about 7, so a 4-year journey to Proxima Centauri as measured on Earth would feel like only about 7 months to the crew. This effect, while potentially advantageous for the crew in terms of subjective travel time, creates a profound disconnect between the travelers and the society they left behind. Decades or centuries may pass on Earth during a journey that feels like only a few years to the crew, and by the time they arrive, everyone they knew may be dead, the political and social landscape may have changed unrecognizably, and the mission they were sent to accomplish may no longer be relevant or desired. This temporal disjunction, sometimes referred to as the twin paradox in its simplest form, is not a defect or illusion, but a real physical consequence of relativity, and it adds a layer of existential strangeness to the prospect of relativistic interstellar travel. Length contraction, another relativistic effect, causes distances in the direction of motion to appear contracted from the perspective of the moving spacecraft. At 99% of light speed, the distance to Proxima Centauri, 4.24 light years as measured in the rest frame of the Sun and Earth, would appear to be only about 0.6 of a light year from the perspective of the crew. This does not change the physical separation or the travel time as measured by external observers, but it does mean that the crew's perception of space and the relationships between events and locations differs from that of observers at rest. The implications of these effects for the crew's experience, their sense of place and continuity, and their ability to coordinate with Earth are subtle and difficult to anticipate without direct experience, which, of course, we do not have. The energy released by a relativistic spacecraft moving through the interstellar medium is also a concern. The kinetic energy of a 1-ton spacecraft traveling at 99% of light speed is approximately 4.4 times 10 to the 20 joules. And if that energy were released suddenly through a collision or a catastrophic failure, the explosion would be equivalent to more than 100,000 megatons of TNT, far larger than any weapon ever created and capable of devastating an area the size of a continent. Even a controlled deceleration, converting the kinetic energy gradually into heat or radiation, would produce enormous power outputs that must be dissipated safely without damaging the spacecraft or its surroundings. The thermal management challenges of such a process are extreme, and any failure to radiate the heat away quickly enough would result in the spacecraft melting or vaporizing. The deceleration problem is, in many ways, the most intractable aspect of interstellar travel. Accelerating to high velocity is difficult, but at least conceptually feasible using external energy sources such as lasers or particle beams. Decelerating, however, requires applying a force in the opposite direction, and in the absence of a convenient energy source at the destination, that force must be generated by the spacecraft itself, which brings back the need to carry fuel or propellant, which increases the mass, which increases the fuel required to accelerate that mass, and so on. One proposal to address this is the magnetic sail, a large loop of superconducting wire that generates a magnetic field strong enough to interact with the charged particles of the interstellar medium, creating drag that gradually slows the spacecraft over distances of light years. The effectiveness of a magnetic sail depends on the density and velocity of the interstellar medium, both of which vary and are difficult to predict along the trajectory, and the deceleration achieved is modest, requiring decades or longer to bring a relativistic spacecraft to rest. Another proposal involves using the destination star's radiation pressure, deploying a light sail oriented to push against the spacecraft's forward motion, but, as mentioned earlier, the luminosity of a red dwarf like Proxima Centauri is too low to provide significant force unless the sail is deployed at extremely close range, within the inner system where the risk of collision with planets, moons, or debris is highest. The possibility of using a relay system, a series of intermediate stations between the solar system and the target star, has been suggested as a way to manage energy distribution and facilitate deceleration. Each station could be equipped with lasers or particle beam emitters to accelerate or decelerate passing spacecraft, breaking the journey into stages and reducing the burden on any single segment of the trip. The construction and maintenance of such a relay network would itself be an enormous undertaking, requiring the deployment of infrastructure across interstellar distances, and the energy and resources required to build and power the stations would rival or exceed those of the missions they are meant to support. The stations would need to be autonomous, capable of self-repair and operation for centuries without resupply, and their positions would need to be precisely known and stable over time to ensure accurate targeting of the beams. The coordination and long-term planning required to establish such a network are staggering, and the initiative would represent a commitment by civilization to interstellar travel as a sustained, multi-generational project rather than a single expedition. The motivations for attempting interstellar travel, despite the obstacles, are varied, and often reflect deeper aspirations about the purpose and future of human civilization. Scientific curiosity, the desire to explore and understand the universe, is one driver rooted in the recognition that the diversity of planetary systems, the conditions under which life arises and evolves, and the ultimate fate of the cosmos cannot be fully comprehended through remote observation alone. Direct exploration allows for the collection of samples, the conduct of in situ experiments, and the discovery of phenomena that are unexpected or undetectable from a distance. The search for extraterrestrial life, in particular, is often cited as a compelling reason to venture to other star systems, with the possibility that Proxima Centauri b or other exoplanets might harbor microbial life, complex ecosystems, or even intelligent civilizations that could transform our understanding of biology, consciousness, and our place in the universe. The detection of life on another world, even if only in the form of microbial fossils or chemical biosignatures, would be one of the most profound discoveries in the history of science, answering the ancient question of whether we are alone and opening new lines of inquiry into the nature of life itself. Another motivation is the survival and expansion of humanity. Earth is subject to existential risks from natural catastrophes such as asteroid impacts or supervolcanic eruptions to anthropogenic threats such as nuclear war, climate change, or ecological collapse. The long-term survival of the human species may depend on establishing self-sustaining populations beyond Earth, diversifying our presence across multiple worlds to reduce the risk that a single event could lead to extinction. Interstellar colonization represents the ultimate form of this strategy, spreading humanity beyond the solar system to ensure that even the destruction of the sun or the entire solar system would not erase human civilization. This perspective views interstellar travel not as a luxury or a scientific curiosity, but as a necessity, a challenge that must be met if humanity is to persist on timescales of millions or billions of years. The ethical implications of this view are complex, involving questions about the responsibility to future generations, the value placed on human survival versus other values, and the rights and interests of any life or ecosystems that might already exist on the worlds we seek to colonize. Economic and resource-based arguments for interstellar expansion are less commonly invoked for the nearest stars, where the distances and costs are so prohibitive that any conceivable return on investment would be delayed by centuries and uncertain in value. However, the long-term abundance of resources in other star systems, including not only raw materials, but also energy from the star itself, could support civilizations far larger than what the solar system alone can sustain. And the expansion into new systems could relieve pressures on Earth and enable a level of prosperity and activity that is otherwise unattainable. This logic applies more readily to within the solar system, where the energy and materials of the asteroid belt, the moons of the outer planets, and the Kuiper belt are accessible on timescales of years or decades, but it extends in principle to the interstellar case if the barriers to travel can be overcome. The psychological and cultural dimensions of exploration also play a role. Human history is marked by exploration and migration, the movement of peoples into new territories in search of resources, opportunity, or simply the unknown. The drive to explore is not universal, and not all cultures or individuals place the same value on it. But for those who do, the challenge of interstellar travel represents the ultimate frontier, the hardest and most distant goal imaginable. The narratives, myths, and stories that arise from exploration have shaped cultures and inspired generations, and the prospect of reaching another star, of standing on the surface of an alien world, and looking back at our sun as just another point of light resonates deeply with the imagination. The symbolic and inspirational value of such an achievement, while difficult to quantify, is real, and should not be dismissed as irrelevant to the practical assessment of whether and how interstellar travel might be pursued. At the same time, the obstacles and costs of interstellar travel raise serious questions about priorities and opportunity costs. The resources, energy, and effort required to mount an interstellar mission are enormous, and they must come from somewhere, diverted from other uses that might have more immediate and certain benefits. The challenges facing humanity on Earth, from poverty and disease to environmental degradation and political conflict, are urgent and tangible. And the allocation of resources to a speculative, high-risk, long-term project like interstellar exploration can be seen as a misallocation, a failure to address the pressing needs of the present in favor of a distant and uncertain future. This critique does not deny the value of exploration, but questions whether interstellar travel, specifically, is the best use of limited resources given the magnitude of the challenges involved and the availability of alternatives. Robotic exploration of the solar system, the development of space-based infrastructure such as solar power satellites or orbital habitats, advances in medicine and biotechnology, efforts to stabilize and restore ecosystems on Earth, all of these represent investments that could yield tangible benefits on shorter timescales and with higher probabilities of success than interstellar missions. The debate over the feasibility and desirability of interstellar travel is not purely technical, but involves values, priorities, and visions of the future that differ among individuals and societies. There's no objectively correct answer to the question of whether humanity should attempt to reach Proxima Centauri or other stars. The answer depends on what we value, what risks we are willing to accept, and what sacrifices we are prepared to make. The technical and physical constraints discussed throughout this examination provide the framework within which such decisions must be made, but they do not determine the outcome. Understanding the constraints is necessary to avoid wishful thinking and to engage with the problem seriously, but it is not sufficient to settle the question of whether and how we should proceed. One aspect of the interstellar challenge that deserves particular attention is the timescale over which progress occurs. The history of spaceflight spans only about 70 years, from the first artificial satellites in the 1950s to the present, and during that time, we have gone from suborbital flights to landing humans on the moon, building space stations, sending probes to every planet in the solar system, and even achieving interstellar space with Voyager 1 and Voyager 2, which have crossed the heliopause and entered the region beyond the sun's direct influence. These achievements are remarkable, but they represent only the beginning of what might be possible, and the pace of progress has been uneven, with periods of rapid advancement followed by decades of stagnation or incremental improvement. The Apollo program, for example, demonstrated that humans could travel to the moon and return within a single decade, but more than 50 years later, we have not returned. And the technology and infrastructure used for Apollo have largely been retired or lost. The reasons for this stagnation are complex, involving political will, economic constraints, shifting priorities, and the inherent difficulty of sustaining large-scale projects over long periods. But the result is a reminder that progress is not inevitable and that capabilities once achieved can be lost if not maintained. Extrapolating from past progress to predict future capabilities is fraught with uncertainty. Some technologies advance rapidly with exponential growth in performance and reduction in cost, as exemplified by the semiconductor industry and the doubling of transistor density approximately every 2 years described by Moore's law. Other technologies, particularly those involving energy, propulsion, and the physical manipulation of matter at large scales, advance much more slowly, constrained by the laws of physics and the difficulty of engineering at the required scales. Rockets, for example, have not become dramatically more efficient in terms of exhaust velocity or mass ratio since the Saturn V. And while reusability has reduced the cost of launching payloads to orbit, the fundamental performance limits of chemical propulsion remain unchanged. Nuclear propulsion, which could offer significant improvements, has been studied and tested in limited forms, but has never been deployed operationally, in part because of technical challenges and in part because of political and regulatory barriers related to the use of nuclear materials in space. The development of new propulsion technologies, from fusion to antimatter to more speculative concepts, requires sustained investment, experimentation, and a willingness to accept risk and failure, all of which depend on the availability of resources and the continuity of commitment over decades or longer. The role of artificial intelligence and automation in enabling interstellar exploration is likely to be significant. Autonomous systems capable of navigation, decision-making, repair, and adaptation without human intervention are essential for missions that last decades or centuries, and where communication delays preclude real-time control from Earth. Advances in machine learning, robotics, and sensor technology are expanding the capabilities of autonomous systems, allowing them to perform tasks that once required human judgment and dexterity. A fully autonomous interstellar probe could, in principle, diagnose and repair its own systems, adjust its trajectory in response to unexpected obstacles or discoveries, prioritize observations based on scientific criteria, and even evolve its mission objectives as new data become available. The development of such systems is ongoing, and while current autonomous spacecraft are capable of basic functions, they are far from the level of sophistication that would be required for true independence over interstellar distances. The integration of artificial intelligence with space exploration also raises questions about the nature and purpose of exploration. If machines can explore on our behalf, what is the role of human presence, and what is lost or gained by delegating the experience of discovery to non-conscious agents? The question of what it means to reach Proxima Centauri or Pluto also warrants reflection. Reaching in the context of space exploration can mean several things. Observing from a distance, passing through the vicinity at high speed, entering orbit, landing on the surface, establishing a base or settlement, or simply transmitting information back to Earth. Each of these represents a different level of engagement and achievement, with correspondingly different requirements and constraints. A flyby mission like New Horizons at Pluto reaches the target in the sense that it gathers data and images during a brief encounter, but it does not stop, does not explore in depth, and cannot return for a second look. An orbiter, by contrast, can study the target over extended periods, mapping the surface, monitoring changes, and conducting repeated observations of specific features, but it requires the ability to decelerate and achieve orbital velocity, a much more demanding task in terms of energy and propellant. A lander or rover can conduct in situ analysis, collecting samples, measuring properties that cannot be determined remotely, and providing a perspective from the surface, but it must survive the descent, the surface environment, and the challenges of operating in conditions that may be hostile or poorly understood. A human presence adds capabilities for real-time exploration, adaptability, and subjective experience, but it also multiplies the complexity, cost, and risk of the mission by orders of magnitude. For Pluto, we have achieved a flyby, and there are proposals for future missions that could include an orbiter or even a lander, though none are currently funded or scheduled. The challenges are substantial, but not insurmountable, and the scientific value of more detailed exploration of Pluto and its moons, particularly in terms of understanding the diversity of planetary bodies in the outer solar system and the history of the early solar system, is recognized. For Proxima Centauri, we have not yet achieved even a flyby, and the gap between our current capabilities and what would be required is so large that it is not clear whether any mission will be attempted within the next several decades or even the next century. The light sail concepts like breakthrough starshot represent the most plausible near-term approach, but they are still in the early stages of development, and it remains to be seen whether the technical challenges can be overcome and whether the necessary funding and political support can be sustained over the decades required to design, build, and launch such a mission. The comparison between Pluto and Proxima Centauri thus serves to illustrate the hierarchy of difficulty in space exploration. Pluto, at the edge of the solar system, is difficult but reachable with existing or near-term technologies, and the obstacles are primarily matters of cost, mission duration, and engineering optimization. Proxima Centauri, at the edge of interstellar space, is difficult in a more fundamental sense, requiring breakthroughs in propulsion, energy generation, material science, and perhaps even our understanding of physics, and the obstacles are not merely quantitative, but qualitative, reflecting limits that are deeply embedded in the structure of the universe. The distance from Earth to Pluto is a stretch, a challenge that tests our ingenuity and resources, but that can be met with sufficient effort. The distance from Earth to Proxima Centauri is a gulf, a separation so vast that it calls into question whether the concept of travel, as we understand it, even applies. The interstellar medium through which any journey to Proxima Centauri must pass is not simply empty space, but a dynamic environment with structure, variation, and hazards. The density of gas and dust varies by orders of magnitude depending on location, from the relatively dense molecular clouds, where stars form, with densities of hundreds or thousands of particles per cubic centimeter, to the voids between spiral arms and the edges of the galaxy, where densities can drop to a tiny fraction of a particle per cubic centimeter. The solar system is currently located within a region known as the local bubble, a volume of space roughly a few hundred light years across that was cleared of dense gas by supernova explosions millions of years ago, leaving behind a tenuous hot plasma with a temperature of about 1,000,000 degrees, but a very low density. The boundary of the local bubble is marked by the increase in gas density as one moves outward into the surrounding interstellar medium, and the trajectory to Proxima Centauri, which lies within the local bubble, passes through regions where the density is relatively low, by interstellar standards, perhaps a few tenths of a particle per cubic centimeter. Even this low density, however, represents a significant number of atoms encountered over a journey of trillions of kilometers. And each encounter, at relativistic velocities, carries the potential for erosion, heating, or damage. The composition of the interstellar medium is predominantly hydrogen, with about 10% helium by number and trace amounts of heavier elements such as carbon, nitrogen, oxygen, and metals, many of which are locked up in dust grains rather than in gaseous form. The dust grains, particles of silicate, carbon, or ice with sizes ranging from nanometers to micrometers, are particularly troublesome for interstellar spacecraft because their mass, though small, is concentrated in solid form. And a collision with a dust grain at relativistic velocity is akin to being struck by a bullet. The cross-sectional area of a spacecraft determines the rate at which it encounters dust, and even a small spacecraft will, over the course of an interstellar journey, intercept many grains, some of which will impact critical components such as instruments, solar panels, or structural elements. The cumulative damage from these impacts can degrade performance, and a single unlucky strike to a vital component could disable the spacecraft entirely. The magnetic field of the interstellar medium, though weak by laboratory standards, with strengths measured in microgauss, plays a role in the propagation of charged particles and the interaction of the spacecraft with the surrounding plasma. A spacecraft moving through the magnetized plasma will experience electromagnetic forces that can, depending on the velocity and the configuration of the spacecraft's own magnetic fields or charge distribution, either accelerate or decelerate the spacecraft slightly, generate drag, or induce currents in conductive structures. These effects are generally small compared to the spacecraft's momentum, but over the vast distances and timescales of interstellar travel, even small effects can accumulate to produce measurable changes in trajectory or velocity. The possibility of using magnetic sails to interact with the interstellar magnetic field for propulsion or braking has been explored theoretically, but the effectiveness depends on the strength and orientation of the field, which are difficult to measure in advance and may vary along the path. The interstellar radiation environment consists not only of galactic cosmic rays, but also of diffuse background radiation across the electromagnetic spectrum, from radio waves generated by synchrotron emission in supernova remnants and the magnetic fields of the galaxy, to the cosmic microwave background, a relic of the Big Bang that fills the universe with a nearly uniform glow of microwave photons at a temperature of about 2.7 Kelvin. At relativistic velocities, the cosmic microwave background is Doppler, shifted and blue shifted in the forward direction, increasing in frequency and energy as seen from the spacecraft's frame of reference. For a spacecraft traveling at 99% of the speed of light, the microwave photons ahead would be shifted into the visible and even ultraviolet range, creating a brilliant glow in the forward hemisphere and subjecting the spacecraft to a continuous bath of radiation that, while not immediately destructive, adds to the cumulative radiation dose experienced by materials and electronics. The energy deposited by this radiation must be dissipated as heat, contributing to the thermal management challenges already mentioned. The absence of reference points and the uniformity of the interstellar medium make navigation a subtle problem. Within the solar system, navigation relies on tracking the positions of planets, moons, and the sun using optical observations, radio ranging, and knowledge of gravitational interactions to determine the spacecraft's position and velocity with high precision. In interstellar space, the sun and nearby stars provide reference points, but their angular positions change slowly, and the distances involved mean that parallax, the apparent shift in position due to the spacecraft's motion, is small. The spacecraft must rely on precise measurements of stellar positions, using star trackers and possibly pulsar timing to determine its trajectory. Pulsars, rapidly rotating neutron stars that emit beams of radio waves with extremely regular periods, can serve as cosmic clocks, and by measuring the arrival times of pulsar signals from multiple pulsars, a spacecraft can triangulate its position in three-dimensional space. This technique, known as pulsar navigation, has been demonstrated in principle and is considered a promising method for deep space and interstellar navigation, but it requires sensitive radio receivers, accurate knowledge of pulsar positions and periods, and sophisticated data processing to account for the effects of the interstellar medium on signal propagation. The question of what a spacecraft would find upon arriving at Proxima Centauri is fraught with uncertainty. Proxima Centauri b, discovered through radial velocity measurements, is known to have a minimum mass of about 1.27 Earth masses, placing it in the category of potentially rocky planets, and it orbits within the habitable zone, where liquid water could exist on the surface if the atmospheric and geological conditions are suitable. However, the planet's actual mass, which depends on the unknown inclination of its orbit, could be higher. And if the inclination is low, the planet could be significantly more massive, possibly a mini-Neptune with a thick atmosphere of hydrogen and helium, rather than a rocky world. The planet's orbital period of 11.2 days implies that it is tidally locked, with one hemisphere perpetually facing the star and the other in eternal darkness, a configuration that could lead to extreme temperature gradients, with the day side potentially hot enough to vaporize any atmosphere, and the night side cold enough to freeze out gases unless winds and atmospheric circulation can redistribute heat. The habitability of such a world is questionable, and it may be that the only regions where liquid water can exist are in a narrow twilight zone between the day and night sides, if at all. The stellar activity of Proxima Centauri poses an additional challenge. Red dwarfs are known for their long lifetimes, measured in trillions of years, far longer than the current age of the universe, because their low masses and slow fusion rates allow them to burn hydrogen for extended periods. However, they are also magnetically active, with strong magnetic fields that drive frequent and powerful flares. Observations of Proxima Centauri have detected flares that increase the star's brightness by factors of several in a matter of minutes, accompanied by intense bursts of ultraviolet and X-ray radiation and the ejection of energetic particles. These flares can strip away atmospheric gases from close orbiting planets, particularly if the planets lack strong magnetic fields to deflect the particles, and the cumulative effect over billions of years could render a planet like Proxima Centauri b sterile and airless. The possibility that life could have arisen and survived in such an environment depends on whether the planet retains an atmosphere, whether it has a magnetic field, and whether life, if it exists, has adapted to the high radiation levels through mechanisms such as subsurface habitats, thick atmospheric shielding, or biochemical resistance to radiation damage. The discovery of additional planets in the Proxima Centauri system adds complexity to the picture. Proxima Centauri c, a candidate planet detected through further radial velocity analysis, may orbit farther from the star with a period of about 5.2 years and a minimum mass of about 6 Earth masses, placing it in the super-Earth category. If confirmed, this planet would likely be too cold for liquid water on its surface, given its distance from the faint star, but it could have a thick atmosphere or subsurface oceans, and it represents another target for exploration and characterization. The possibility of additional planets, moons, asteroid belts, or cometary populations in the system means that a mission to Proxima Centauri could encounter a complex and diverse planetary system with opportunities for comparative planetology and the study of system architecture, but also with increased hazards from debris and gravitational perturbations. The detection and characterization of exoplanets have advanced dramatically over the past few decades, with missions such as Kepler, TESS, and ground-based surveys discovering thousands of planets around other stars, revealing that planetary systems are common and diverse. The methods used to detect these planets, including transits, radial velocity, direct imaging, and gravitational microlensing. Each have their strengths and limitations, and the data they provide are often incomplete, giving only some of the parameters of the planet's orbit, mass, radius, or atmospheric composition. The next generation of telescopes, including the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and ground-based extremely large telescopes, such as the European Extremely Large Telescope and the 30-meter telescope, will improve our ability to characterize exoplanets, measuring their atmospheres, searching for biosignatures, and refining our understanding of their properties. But even the best telescopes operating at the cutting edge of technology cannot provide the detailed, high-resolution, in situ data that would come from a spacecraft actually visiting the planet, landing on its surface, and conducting direct measurements. The gap between remote observation and physical presence remains, and it is this gap that defines the difference between knowing about a place and being there. The question of whether humanity will ever reach Proxima Centauri is not one that can be answered with certainty. The obstacles are immense, rooted in the physics of energy, velocity, distance, and time, and they cannot be overcome by incremental improvements alone. What is required is either a fundamental shift in our capabilities through breakthroughs in propulsion, energy generation, or material science that open new regimes of performance, or a transformation in our approach to exploration, accepting multi-generational timescales, autonomous systems, and the possibility that the missions we initiate may not yield results within our lifetimes or even within the lifetimes of our civilizations as we know them. The choice to pursue interstellar exploration or not is ultimately a choice about what kind of species we want to be, what legacies we want to leave, and what risks and sacrifices we are willing to accept in the pursuit of knowledge and survival. Pluto, by contrast, is a destination we have already reached, if only in passing, and it represents a more accessible frontier, a place where the challenges are difficult, but solvable with sustained effort and investment. The exploration of Pluto and of the outer solar system more broadly offers opportunities to study the formation and evolution of the solar system, to understand the diversity of planetary bodies, and to search for prebiotic chemistry or even life in the subsurface oceans of moons like Enceladus or Europa. These goals are scientifically rich and achievable within human timescales, and they provide a pragmatic focus for near-term space exploration efforts. The expansion of human presence within the solar system, from the establishment of bases on the Moon and Mars to the mining of asteroids and the construction of orbital habitats, lays the groundwork for the long-term capabilities that might eventually enable interstellar travel, but it also delivers tangible benefits and knowledge in its own right. The relationship between near-term and long-term goals in space exploration is not one of simple progression, but of mutual reinforcement. The technologies, infrastructure, and experience gained from exploring the solar system contribute to the knowledge base and industrial capacity that would be needed for interstellar missions, and the vision of interstellar travel, even if distant and uncertain, provides a sense of direction and purpose that can motivate and sustain efforts over decades. But the pursuit of the near-term goals does not guarantee that the long-term goals will ever be achieved, and the focus on immediate challenges can sometimes obscure or defer the larger questions of feasibility and strategy. The balance between ambition and pragmatism, between dreaming and doing, is one that each generation of explorers and planners must navigate for themselves. The physical limits that govern space travel are not arbitrary constraints imposed by human ignorance or lack of ingenuity, but are expressions of the fundamental structure of the universe, the relationships between matter, energy, space, and time that are codified in the laws of physics. These laws have been tested rigorously through experiment and observation, and while they are subject to refinement and revision as our understanding deepens, they have proven remarkably robust across a wide range of scales and conditions.